So we're given velocity, and we're asked for something about its change in location. So we want to know displacement. So that means we're going to want to integrate from 0 to 25 of the velocity function. So to do that, it might be easier to rewrite the velocity function. If I multiply this parentheses to itself, that's going to give us 64 minus 16 square root of t, because it's going to be negative 8 square root of t minus 8 square root of t. Oh, wait, sorry. Those are multiplying to each other, so that'd be minus 16t. No, I was right the first time. It's not multiplying yet. I should have just wrote it out, but if you do this times this, should be what I'm getting up here. Because negative square root of t times negative square root of t gives us positive square root of t. Positive t, I should say. Okay, and then we can distribute that square root of t to each term. So rewriting this expression, we should have 64 square root of t minus 16t plus t to the 3/2, or the 1.5 if you want. And that's easier to integrate because to find the antiderivative, we can go term by term. This is a 1/2. If the power goes up by 1, now it's going to be a 3/2 power. We've got to multiply by the reciprocal of that power to make sure that the derivative of the antiderivative turns back into what we started with. So it's 3/2 now. And then here, the power goes up by 1. Did I do that right? That should be square root of t, right? Oh, no, because I distributed. Okay, so that's going to be 8t squared. And then here, that's going to be 2/5 t to the 5/2, because the power goes up by 1. And then no arbitrary constant, because we have limits of integration. And it doesn't matter what happens. When you plug in 0, the whole thing turns out to be 0. So luckily, we just have to worry about plugging in 25. So the first term, I get 5,333.333 repeating. It's 25 squared times 8, so that's this minus 5,000. And then we've got 25 to the 2.5 power times 2 divided by 5. I want to add that to the previous result. So I got 1,583.33 for the first answer. Then how far does it travel during the first minute? I think the only difference here is the limits of integration. It's in terms of seconds, so that's 60 seconds for the same thing. So we're just basically doing this part again, except 60 instead of 25, as far as I can tell, unless I missed something. So 60 to the 1.5 power times 64 times 2 divided by 3. And then next term, doing 60 squared times 8. Oops. Here. 60 squared times 8. So I want to subtract 28,800. Okay, we're in the negatives. Oh. Well, how far does it travel? Because it looks like it's going forward and backwards since I'm getting some negatives. Here, we'll have to check that out in just a second. Let me see. Finish plugging this in. So 2,183.87 when I round. Let me take a look here. Okay, no, luckily I was overthinking it a bit. I was wondering if they meant the total distance traveled during the first minute. That would mean the distance it went backwards plus the distance it went forward. So we'd have to analyze that function a bit. Last part, how far is it gone when it momentarily slows to a stop? If it's slowing to a stop, that means the velocity is 0. So you can plug in 0 in here and solve for all the values of t that would make that be true. There's 2, I think, right? Because when t equals 0, it's stopped. And then if we solve this equation by setting it equal to 0, then we get 8 equals square root of t. We can square both sides, so t would be 64. Yeah, because if you plug in 64, square root of 64 is 8. 8 minus 8 makes 0. So it momentarily slows to a stop at t equals 64. So that last part, you just want to do the same integral, so it's going to have the same antiderivative, except you're plugging in 64 instead of 60. So same thing, plugged in 64 times 2 divided by 3. There's my first term. 32768. 64 to the 2.5 times 2 divided by 5. So I got 2,184.53.